Hi, welcome back from lunch. I'm really excited to introduce Xiao Ling. Xiao Ling is now at Apple, working on knowledge bases in Siri. He got his PhD from University of Washington, which is where we overlapped for a couple of years. He's done some seminal work, I would say, in information extraction, especially in fine-grained entity types that are increasingly becoming popular. And he's written some really insightful papers on entity linking and how to approach them basically from fundamentals. So I'm really excited to see what he's doing at Apple. Let's all welcome him.
Thanks, Samir. Check. OK, all right. Cool. So what is Siri Knowledge? A number of you might be wondering. Let me tell you a real story. I met Tom Dittrich, who is a renowned machine learning researcher at Oregon State. I met him at AAA this year in Hawaii. And I read quite a number of papers of his, and I'm really excited to tell him what we have been working on in Siri Knowledge. I took out the phone from my pocket, and I demoed a couple questions that we answered as Siri. And his reaction was, "This is great. Isn't this powered by Google?" So if there is only one key takeaway I would like you to remember out of this talk is we're just like you. We are very interested in building a capable, comprehensive knowledge graph at Apple. And we use this knowledge graph to power our question answering component and capability so that we can assist our users on all those Apple devices. Let me show you what I meant by open domain question answering. It's more, actually the term is sometimes overloaded, but what we really meant is some factoid question understanding. For example, on an iPhone, you can actually ask questions such as how many Super Bowls has a sports team won, where did Barack Obama go to school, who were the members of the Beatles, as well as how many calories are there in an apple. So Siri Knowledge powers all those Apple devices. Additionally, we also support Spotlight. If you use an Apple device, you can see the Spotlight functionality. All those sections are powered by our team. We also enable some functionality if you use macOS. For example, if you're reading a news article and you want to highlight a particular phrase so that you can actually look it up and see some facts about her. Lastly, if you're actually using Safari and we're trying our best to answer any queries you type in the address bar. So in the rest of this talk, I would like to tell you more about our knowledge-based construction efforts. I will start with an overview of the approach that we took, and I will dive into more details in 3 concrete problems. So the overall approach we took was not completely new. We adopted a lot of best practices in the literature. So basically, we treat knowledge-based construction as a data problem. We have a bunch of data inputs, and we build models to understand them, disaggregate them, process them. We generally categorize all those data inputs into 4 categories: unstructured, semi-structured, structured data, as well as human curation. The human curation part allows us to add manual data inputs as well as a correction of extraction errors. Once we have the outputs of all those data inputs, which are all represented by just canonical triples. When I say canonical triples, I really meant subject, predicate, object, all represented by unique identifiers. So there is very little ambiguity there. Once we have this collection of triple sets, we build this knowledge fusion component so that we can consolidate those triple sets as well as resolving conflicts among all those data sources. As most of us know, that no knowledge base is complete, so we're trying to we have been building a knowledge completion module so that we can actually derive new facts from existing ones. for the sake of simplicity and avoiding using internal code names, I'm going to use Wikidata to refer to our knowledge graph, so it's more accessible to the audience, and I don't violate any confidentiality contracts. All right, let me start with the first category of data inputs, the natural language text. Apple Music is actually one of the key businesses at Apple, and we want to build a comprehensive knowledge base so that we can cover most of the music-related facts. And one of the key type of facts is band membership. So we started looking at the existing facts in our knowledge graph. They do have a good coverage, but they don't actually they're actually missing out some key facts. For example, here's a sentence: in early 1980, Crover moved to San Francisco, but recommended Dave Foster to the band as his replacement on drums. So Yejin, a few of my colleagues and I have been working on building this system so that we can go end to end from Wikipedia articles in natural language text to canonical triples in the end. If you're familiar with TAG-KBP, this is very similar to that problem setting. For each of those components in between, we follow a very generic knowledge-based construction workflow, where a knowledge-based construction engineer starts with generating a set of candidates in a high recall setting. The candidate definition varies from task to task, but we usually create a bunch of features to represent each candidate. We heavily depend on distance to vision and data programming to train our models, and use the trained models to make predictions over unlabeled examples. And there is one key part, which is the last step of this loop, which is error analysis. We build extensive tools to allow our KBC engineer to look at the results, bucketize the errors so that they can iterate the model and improve the quality. Let me quickly go through what I meant by each component. We start with mention extraction, which is more than just name entity recognition. We try to identify the entity mentions of name entities, as well as common noun phrases and pronouns. And the color indicates the entity type of that particular mention. And we followed by a relation extraction module where we try to classify the relationship between arbitrary pairs of entity types in the same sentence. We also build a coreference resolution system so that we can understand those pronouns and common noun phrases and cluster those mentions into sets, and each set represents a real-world entity. In this case, we don't have any literal values such as dates or numerical values, so we only need to run entity linking to link those mention clusters into a unique identifier in the knowledge graph. So this is what an output triple looks like. Basically, we have an ID of Nirvana, we have an ID for the relation type has member, and we have the ID for Dave Foster. In addition to that, we try to create what's called qualifier, so that we can actually create relations that are conditioned to an existing triple. So in this particular case, we also build the extraction models to extract qualifiers so that we know this particular fact of Dave Foster being a member of Nirvana only started in 1988. In total, in our production system, we actually generate, we extract more than 2 million facts in an over 95% precision. Moving on to the second type of data inputs, which is semi-structured data. What we meant by semi-structured data is the data which is usually syntactically structured, such as by HTML text, but not semantically annotated. For example, the cell texts are still just strings. One of the representative examples is infobox, Wikipedia infoboxes. So we have been, Yejin, Eric, Vivek, and Azadeh have been working on this problem for a while, and we have published a paper in NACO this year to tell people about our findings. The problem is really simple. So basically, you have input of those Wikipedia info boxes either in HTML or in the underlying Wikimedia code that's used to render such HTML. So this is not a new problem. It has been studied before, and it has been largely thought of as a solved problem. But when we actually look at the literature and start using the DBpedia tool, let me just clarify. By DBpedia, I meant the DBpedia extraction tool rather than the DBpedia knowledge base, because the knowledge base is more than just from Infobox. The DBpedia extraction tool is implemented as a deterministic mapping from the underlying media wiki templates, and two main drawbacks are: one, it's not very scalable to new templates because they require a human addition of the mapping. And also, they're very brittle to template changes. If the underlying media wiki template changes, for example, one field's birth date is changed to a date of birth, then the mapping automatically breaks. Additionally, the DBpedia extraction tool has been heavily dependent on existing anchor links in Wikipedia articles. So in this particular case, when you look at the anchor link of Malia, it actually links to the family of Barack Obama rather than the Wikipedia page of Malia Obama. Also, the tool is not very sensitive or friendly to those unlinkable entities. If you're familiar with AKBC setting, they're usually called the neo entities. But if you're not, they're just entities that you don't really have an existing knowledge-based entry so you can link to. So in the paper, our main contributions are, one, we build a robust infobox extraction system. We use HTML as input because then we cut the dependency from the template, because HTML is always rendered by the Wiki Foundation code. We also use distance supervision so that we can actually easily retrain those models for extraction. We were able to improve F1 significantly over the DBpedia extraction tool. Also, we look at a more strict metric. We call it completeness over list value relation types. We look at this particular metric because research communities have been very tolerant of maybe if you miss one entity for a particular subject predicate pair, it's probably fine. But if we miss one particular extraction, let's say if we mistakenly extract 3 children for Barack Obama, then the press or the social media would be all over us. So that's something that we really want to focus on. Again, just a quick recap of the workflow that we follow for the same extraction for this infobox extraction problem as well. The system is divided into 2 main components. We start with relation extraction. In this semi-structured data extraction problem, the subject is kind of trivial. It's usually just the title of the Wikipedia page. So we focus on the object mention. We generate a bunch of candidates, and we represent all those candidates by their features. We use distance supervision to create training examples. Huaifeng has done a great job explaining all the details. Let me just quickly, briefly mention what distance supervision is. It's basically just use some existing structured data records to heuristically match with unlabeled examples so that we can automatically create those training labels. Once we train the model, we treat each relation type as a binary classification problem. Then we apply the trained models over unlabeled examples and produce those triples. Now that we have those triples, both subject and predicate are disambiguated. They're represented by unique identifiers. The object is not yet. So we build a interlinking module so that we, following same workflow, candidates, features, distance supervision through anchor links as well as some heuristic rules. We are able to build classifiers so that we can make predictions over unseen links, as well as telling if the entity is unlinkable or not. So this is how we actually compare our system with the DBpedia baseline. We pull the extractions from both the system we built, RIPE, as well as the DBpedia extraction output. We have human annotators look over samples from both systems and form a ground truth based on each entity. based on a set of entities. The metrics we use are pretty standard, precision recall F1, and I already explained the completeness. Just a quick recap. If we don't extract exact same set for a particular subject and predicate pair, then we actually get a score of 0 in this particular metric. When we look at the results, DBpedia actually did fairly well in precision, and RIPE is really doing much better in recall as well as the list value relation type completeness. A quick summary of what we did for infobox extraction. We built a system called RIPE, which is robust to template changes as well as new templates. We actually, through careful design choices, we were able to improve both precision and list value relation type completeness significantly over a strong baseline. The last data input class I want to talk about is structured feeds. So I think most of us are interested in the information extraction problem setting from natural language text. So this is from structured feeds. Usually the problem is studied in the database field. Our motivating example is, again, I use a music-related example. So when we launched the HomePod, which is an intelligent speaker, we try to provide a musicology feature so that the users, while listening to music, can ask questions about who plays the music, if it's a band, who were the members, etc., etc. And the Apple Music is typically powered by typically by the iTunes Store. Therefore, those songs and artists, they're tracked by iTunes IDs. But iTunes doesn't focus on the biographic information of those musical artists, whereas we do have plenty of such information, as I mentioned earlier from the first two problems. So now the problem is how we actually connect two knowledge bases, the iTunes catalog as well as our knowledge graph. In the literature, it's typically called interrelation or record linkage or deduplication. The problem really is you have multiple data sets with data records referring to the same real-world entities. And your goal is to identify those data records that are really equivalent to each other. So in our real setting, we have one technical challenge, which is when you look at Wikidata, when you look at Wikidata, you have tons of biographic information, but when you look at iTunes, it doesn't really match. Then the only thing that you can use to match those entities is the name. And as we all know, names are ambiguous. Our solution to this problem is actually to make it more complicated by introducing a third knowledge base for this anti-resolution problem. The third knowledge base is a musical vertical knowledge base called Music Brains. It has a bit of both sides. Has some biographic information good enough for us to run anti-resolution to match entities with Wikidata, and it has some musical information as well, although not as complete as iTunes. So what we did is we first run anti-resolution between Music Brains and Wikidata, and we merged them into a new knowledge base, and then run anti-resolution between the merged one and iTunes, so that we can actually connect all three knowledge bases. Because equivalence is transitive, therefore we can actually say the iTunes ID is equivalent to that Wikidata ID. We also evaluated our production system, and we created two test sets. One is we look at all those popular artists, and we also create a random sample. Over both data sets, we were able to achieve over 95% precision for the problem of predicting the Wikidata ID for a given iTunes ID. The precision recall is defined similarly as an entity linking problem, so that if you mispredict a particular particular Wikidata ID, then you will be penalized as a false positive as well as a false negative. So once we finish that problem, then we also get another request from Apple Music, which is we want to be able to answer questions such as who plays piano in a particular song. None of the three knowledge bases that we actually look at contains a good coverage of such information. So what we need to do is we actually included a fourth knowledge base in this entity resolution problem. And the challenge there is now we need to run entity resolution over not only just artists, but also songs. So we need to understand this Discogs, Welcome to New York ID is equivalent to which iTunes ID. Also, as you may notice, all those instruments are represented by strings, so we need to implement an entity linking system to understand that. And of course, we also need to resolve those artists. Just a quick recap, we want to connect all those knowledge bases so that we can enable more applications for our users. The solution to that is we build entity resolution systems so that we can actually predict those equivalences between IDs of all those knowledge bases. For a particular problem of resolving the entity equivalences between iTunes and Wikidata, there is very little data that we can actually reliably use to match. So we actually use a bridge knowledge base to solve that problem. And lastly, when we want to provide some credit information to the users, we actually need to do entity resolution for more than just one entity type. All right, the key takeaways I like to summarize is the following. I have been using music-related examples so that we can actually understand a problem, but we really try to be know-it-all rather than just know music well. And for all those information extraction problems or KBC problems, we try to follow the developer workflow so that we can quickly and iterate our models. For the natural language extraction problem, we've implemented a production system that's able to achieve over 95% precision in music-related extraction. And we also demonstrated that through careful design choices, we can actually improve a largely thought solved problem significantly in terms of F1 and list value completeness. The third problem I talk about is Entero resolution, which enables us to connect all those knowledge bases, all those data sets, internal and external, so that we can actually enable all those applications or questions so that we can answer from user. So I want to spend maybe a couple minutes on future directions we have been looking into. So I kind of implicitly stating that all the data sets we've been looking at are textual. But we're also looking at trying to look at videos, images, and create a multimodal knowledge graph. Because our ultimate goal is to represent all human knowledge in the knowledge graph. The second direction we want to look at is actually being able to automatically generate entity descriptions, because we want to provide a human-readable description of those entities, because we need to present those answers to the user. And because of entity resolution, there are lots of open domain entities which lack a proper entity description. So it's a kind of a challenging natural language generation problem here. And the third one, which is future direction or slash work in progress, is I've been talking about this workflow with, and we observe that most of our time is actually spent in those feature engineering. As most of us already know, the advance in deep neural nets in the past few years actually has proven its effectiveness in a lot of tasks. And Chris, Fun, and Pablo have been taking maybe a step even further. They are trying to build a multitask learning, a modular learning framework, which led the developers to focus on the task specification rather than the architecture. The framework is architecturally agnostic, so basically through specs, you can actually define all those modules, LSTM, transformers, whatever you want, and focus on the job descriptions, feeding those supervisions, iterating those models so that we can actually ship machine learning KBC systems to production. as a matter of fact, they have already shipped a question answering model using this framework in production in many languages. Let me just give you a very brief view of some preliminary results that we have been using this framework for the anti-evaluation problem that I just talked about. So again, the challenge. The challenge is really we want to cut the feature generation part because that's the most time-consuming step, and we've been using this new framework and building the models for the exact same problem and evaluating over the exact same data sets, and with significantly reduced developer time, we were able to produce models that are as good over the popular artist set, and significantly improving the recall over a random sample without sacrificing in precision. With that, I want to just say, none of this work is possible without my great colleagues. And Yejin, Eric, and Vivek, they're actually attending the conference. If you don't believe me, you feel free to reach out to them and ask about what we're actually doing. And shameless plug, we're hiring. So if you're interested, feel free to find me offline. And I thank you for listening to the talk and happy to take questions.
Hi. When you're doing entity linking across knowledge bases, what do you do when you don't have labeled data for that?
When we don't have...
If you don't have labeled data for across the knowledge bases,
cool.
How do you...
Right. Very good questions. I guess there are two ways to solve that. One is sometimes there are some existing links. For example, if you look at Wikidata, there are some existing links to iTunes. We leverage that for training examples. We also collect some of those examples in-house because there's just no way to generate distance coefficient in this particular setting. But the number of training examples we collect is usually just in hundreds or maybe thousands, not in an excessive number.
Thanks.
Hello?
Yeah.
Yeah. Could you tell us a bit more about the, you showed the improvement in kind of recall when you moved to the different modeling environment. Could you explain a bit more about, I wasn't that clear about what drove that improvement. Could you explain a bit more about the kind of things you're doing there that improved that?
Right. So we have been. So the existing system in production is heavily reliant on manually created features, and we have been covering the popular set pretty well, the head, but we haven't been creating a very extensive feature library to cover the tail. That's why we didn't do very well in recall for the random sample. Whereas the new framework, which is over deep learning, then we don't really need to manually create such features, and it's automatically learned. So the feature implementation learned from this framework is able to cover some of more on the tail data than the manually created one.
Thanks.
Hi. So I really enjoyed your talk, and I wanted to know, since Apple is a private enterprise, and you're trying to create a knowledge base that kind of answers open-ended questions, where in your pipeline are you like employing safety features for, say, controversial questions?
Oh, that's an excellent question. So let me just repeat the question so that I make sure I understand the question. Are you asking about if there are some facts that are maybe disputable?
Facts that are disputable, or just questions where maybe not all users should be privy to the answer. For instance, imagine someone asking a question like, how do I kill someone else? Maybe you don't want to publicly display several results for the question.
Right. Yeah, that's a great question. We actually, what I've been talking about is mostly on the engineering, on the extraction side. So we let those facts to live in the knowledge graph, but how we present the answer is another kind of team or another problem. We have extensive human interaction, conversation interaction reviews to kind of cover those, for example, disputed territories or some harmful questions or harmful topics. There are extensive human reviewing to prevent those answers to be presented to the user.
Yeah, so it's not on the basis of the data that you're collecting, and when you're building your knowledge graph, you're agnostic to what kind of questions might come.
Currently, yes.
Okay.
So the implement system is agnostic, but when we actually present the answer, there's another layer to kind of filter out those questions that are sensitive.
Thank you.